Welcome. If you work in automotive engineering, you have probably heard about ISO 26262. But what exactly is this standard? Why is it so important for modern vehicles? And what do engineers actually do when they apply it in real projects? In this video, I will explain ISO 26262 in simple terms. We will look at why functional safety matters, what the standard covers, and the most important concepts engineers should understand. Let's start with a simple question. Why do we even need functional safety in modern vehicles? Modern vehicles are highly complex systems. A single car may contain dozens of electronic control units and millions of lines of software code. Many of these systems directly influence the behavior of the vehicle. For example, the braking system, the steering system, or the airbag controller. Now imagine that one of these systems behaves incorrectly. A sensor provides wrong data, a control unit fails, or a software component crashes. What could happen? In some cases, the result could be a hazardous situation. And this is exactly why functional safety is so important. To manage these risks, the automotive industry developed the standard ISO 26262. ISO 26262 is the international standard for functional safety in road vehicles. It focuses on electrical and electronic systems inside modern vehicles, including the software running on those systems. The goal of the standard is to reduce risks caused by malfunctioning behavior. In other words, ISO 26262 provides a structured framework that helps engineers design safer systems. But to understand this better, we first need to clarify one important concept. What exactly is functional safety? Functional safety is a specific part of overall system safety. It focuses on hazards that arise when systems do not behave as intended. In other words, we are not looking at normal operation. We are looking at failures. For example, imagine a braking system that suddenly activates without driver input. This is a malfunction. If that malfunction creates a hazardous situation, engineers must ensure that the system either prevents the failure or controls its consequences. Functional safety is therefore about identifying possible failures, analyzing the risks they create, and defining measures that reduce those risks. So how does ISO 26262 actually organize safety work? The standard follows what is called a safety lifecycle. Instead of looking at safety as a single activity, ISO 26262 treats safety as something that must be addressed throughout the entire development process. It starts in the concept phase, where engineers identify hazards and define safety goals. From there, safety requirements are developed and implemented at the system, hardware, and software levels. Even production and operation are part of the life cycle. This life cycle approach ensures that safety is not treated as an afterthought. Instead, it becomes an integral part of the engineering process from the very beginning. But before engineers can define safety requirements, they first need to understand something fundamental. What could actually go wrong? ISO 26262 is a fairly large standard, and it is divided into multiple parts. For a first overview, a few of these parts are especially important. Part 2 focuses on functional safety management. This includes planning, responsibilities, and safety culture. Part 3 covers the concept phase, where hazards are analyzed and safety goals are defined. Part 4 addresses system-level development, where safety requirements are allocated to system elements. Part 5 focuses on hardware development, while Part 6 addresses software development. Together, these parts guide engineers through the safety-related activities of the development process. But one of the most critical activities happens very early in the life cycle. This is the hazard analysis and risk assessment. During the concept phase, engineers perform an activity called hazard analysis and risk assessment, often abbreviated as HARA. The goal of this activity is to identify hazardous events related to the system being developed. Engineers start by defining the system, which ISO 26262 calls the item. Then they analyze possible hazards that could arise if the system malfunctions. For example, a braking system might fail to apply braking force when needed, or it might apply braking unexpectedly. For each hazardous event, engineers assess the risk. Based on this analysis, they define safety goals. These safety goals describe what the system must achieve in order to prevent hazardous situations. But once a hazard is identified, another important question must be answered. How critical is this hazard? Once hazardous events have been identified, the next step is to determine how critical they are. ISO 26262 does this using the Automotive Safety Integrity Level, or ASIL. ASIL represents the level of risk reduction that must be achieved during development. The standard defines 4 ASIL levels, from ASIL A to ASIL D. ASIL D represents the highest safety integrity level. Higher ASIL levels require more rigorous development processes, stronger safety mechanisms, and more extensive verification activities. Some functions may not require a specific ASIL. In those cases, standard quality management processes are considered sufficient, and the function is classified as QM. But how exactly is the ASIL level determined? The ASIL classification is determined using 3 parameters. The first parameter is severity, which describes how serious the potential harm could be. For example, minor injuries would represent a lower severity than life-threatening injuries. The second parameter is exposure. This describes how frequently the operational situation may occur. The third parameter is controllability. This refers to the ability of the driver or other road users to avoid the hazardous event. These parameters are combined using a structured evaluation table defined in ISO 26262. The result of this evaluation determines the ASIL level for the hazardous event. Once safety goals have been defined, they must be translated into concrete engineering requirements. Safety goals typically describe the overall safety objective. However, they are not detailed enough to be directly implemented. Therefore, engineers derive functional safety requirements. These requirements describe the functions needed to achieve the safety goals. From there, technical safety requirements are developed. These technical requirements define how safety measures will be implemented within the system. An important aspect here is traceability. Every safety requirement should be traceable back to the hazard it is intended to mitigate. After safety requirements have been defined, they must be implemented across the system. At the system level, engineers define the architecture and allocate safety functions. At the hardware level, potential random hardware failures must be analyzed and mitigated. At the software level, development processes focus on preventing systematic faults. Verification and validation activities are performed throughout the development process. These activities ensure that safety requirements are correctly implemented and that the system behaves as intended. Let's look at a simplified example. Consider an airbag system. The purpose of the system is to protect vehicle occupants during a collision. However, one potential hazard could be unintended airbag deployment. If the airbag deploys unexpectedly while driving, it could startle the driver or cause loss of vehicle control. During the hazard analysis, engineers evaluate this hazardous event. They assess severity, exposure, and controllability. Based on this analysis, an ASIL level is assigned. From there, safety requirements are defined to ensure that the risk is reduced to an acceptable level. ISO 26262 provides a structured framework for managing functional safety in automotive systems. It ensures that hazards are systematically identified and analyzed. It supports structured risk evaluation and clear decision-making. Safety goals and safety requirements are defined in a traceable way. And verification activities provide evidence that the system meets its safety objectives. This structured approach helps organizations develop complex automotive systems with a higher level of confidence in their safety. Let's summarize the key ideas from this overview. ISO 26262 is the international standard for functional safety in automotive systems. It focuses on risks caused by malfunctioning behavior. Hazard analysis and ASIL classification are central concepts of the standard. Safety goals and safety requirements guide the engineering implementation. And most importantly, safety activities span the entire development lifecycle. Understanding these fundamentals is the first step toward working effectively with functional safety. If you would like to explore ISO 26262 in more detail, I have created a complete training course on my website. In that course, I explain the safety lifecycle, hazard analysis and risk assessment, ASIL determination, and many of the practical development activities engineers perform when working with functional safety. You can find the link to the course in the video description and also in the pinned comment below. And if you found this video helpful, feel free to give it a like and consider subscribing to the channel. I will be publishing more videos explaining important engineering standards such as ISO 26262, ASPICE, ISO 14971, and other topics related to safety critical systems. Thanks for watching, and I hope to see you in the next video.